If you would recall, we've been looking at differentiation and integration and how they're related. We've talked about the fundamental theorem of calculus and how we can use the fundamental theorem of how the fundamental theorem of calculus states that we can calculate a definite integral using an antiderivative, and we can also construct an antiderivative using the definite integral. This is good because not all functions have nice antiderivatives, and so it's useful to be able to construct an antiderivative if we need to. And since we're just constructing an antiderivative with a definite integral, and a definite integral is represented by area, we can construct an antiderivative just by calculating area. And area is something that we can always calculate to any degree of accuracy, subject to the limitations of the data that we have available. So, all very useful stuff. But we want to look at some applications, and we're going to start with the Calc 1 favorite application, position, velocity, and acceleration. The reason that we want to do this is that derivatives are about rates of change, and position, velocity, and acceleration are all rates of velocity is the rate of change of position, and acceleration is the rate of change of velocity. So it gives us a nice setup with an application of a function, its first derivative, and its second derivative. Since velocity is the derivative of position and acceleration is the derivative of velocity, we go from position down to acceleration by doing derivatives. Since integration is almost the inverse of differentiation, the inverse operation of differentiation, if we start with acceleration, we can integrate to get to velocity, and then we can integrate the velocity to get to position. So let's do our favorite example of this projectile motion, just gravity. So this is the category of our favorite example. I'm going to phrase this in the form of a differential equation. So our favorite example is just dropping stuff, having stuff fall due to gravity. So here's how we say it. Acceleration due to gravity is constant. Acceleration due to gravity is constant. So this requires some constraints. So we're just going to be on Earth doing these problems. The further we get away from Earth, the less gravity we will experience. But as long as we stay close to Earth, gravity is constant. It's not going to change that much. So this is once again using that calculus thinking. For continuous functions, if we look close enough, it's not going to change that much. So we're going to set it up this way. Acceleration due to gravity is constant. Acceleration is the second derivative of position. So it's the first derivative of velocity. And so what we've stated here can actually be reframed as a differential equation. So we're going to write this statement as a differential equation. A differential equation is an equation, no surprise there, involving differentials. That's a terrible way to do it. Although that harkens back to one of my favorite sentences in any math book ever. My favorite sentence from any math book was from a pre-calculus textbook, and it was highlighted in blue. And the sentence was, a nonlinear function is a function that is not linear. I was like, oh, fucking A. Thank you for making a whole separate box, highlighted in blue, to essentially tell us what non means. And I can't tell if the author was serious or not. But then I thought about it for a long time. It's like, oh, all right, I get the message. I get the subtext. The subtext is just state the obvious thing. You don't know where we all came from. Just state the obvious thing. So I'm going to do that. That became, I try to state the obvious thing whenever I can. Because things that are obvious to me are not necessarily going to be obvious to you. That's why you hired me in the first place, right? I know some stuff. You want to know some stuff that I know. So you hire me to tell you that stuff. So anyway. So a differential equation is an equation involving a function and its derivatives. A differential equation is an equation involving a function and its derivatives. A differential equation is an equation involving a function and its derivatives. In the equation, the unknown, the thing that you're solving for, is the function. The goal is to solve for the function that fits the description. This is a different type of equation that we've encountered in the past. Equations in the past have been find the variable that fits the description in the equation. Here we're not looking for a variable, we're looking for a function. We have a description of some function. The reason that differential equations are important is that differential equations are how we describe things. We make observations, and the observations give us information that we about how something is changing. So perhaps we observe how something that we're trying to study is changing. We come up with a hypothesis, and then we encode that hypothesis in a differential equation. So, for example, maybe we observe that acceleration due to gravity is constant. As an apple fell on our head or whatever. I don't know. Has anybody heard? I don't know if that's a common story anymore. There are all these apocryphal stories that people come up with. Like Descartes came up with coordinates because there was a fly walking along the ceiling. It's like, X and Y coordinates. And Newton came up with gravity, how gravity works because the apple fell on his head. Einstein is bad at math. They're all like weird things that we all just collectively believe. You know what I mean? Has everybody heard that one? Einstein was bad at math. Einstein wasn't bad at math. He was perfectly acceptable at math. When he complained about the math that he had to do, it's because they had to invent new shit for the ideas that they were dealing with. So really, when he said, "Don't worry about your troubles in mathematics, I assure you mine are greater," that's really just like, that's kind of a dick quote. Because he's like, oh, you think you got problems. That's what that quote translates to. That's the energy in that quote. You think you got problems? You should see the shit that I have to deal with. That's a dick quote. Anytime that's your energy, you're being a jerk. Knock it off. I'm just kidding, Ghost of Einstein. Stop haunting me. He doesn't haunt me. I did an exorcism. I'm just kidding. He's still haunting me. And he makes fun of my shitty math skills. He taught himself calculus. That's the thing. The problem is They say he was bad at school. Being bad at school and bad at math are 100% not the same thing. School is a separate skill. Being good at school, that's a separate skill. You know what I mean? For the most part, being good at school means having the most important characteristic, for example, of an American school student. What's the most important characteristic of an American school student? Y'all are demonstrating it right now. Compliance. Shh, stop, be quiet. That's it. Right? Because as soon as you start speaking up, that's when we apply the phrase. You know how they say things like the squeaky wheel gets the grease? We say we observe the exact same thing with different energy by saying the nail that sticks up gets hammered down. And that's what schools want. They want you to be there and be quiet and do your stuff. Or not, as long as you're quiet while you're not doing your stuff. Do you know what I mean? Anyway, this is why we care about things like differential equations, because this is how we'll make observations. We'll observe how things are changing, and we'll make some hypotheses about how those things are changing, and then encode it. And so one thing that we encoded is that acceleration due to gravity is constant as long as we stay close enough to Earth. Like ignoring air resistance. As long as we don't throw things very hard, air resistance is not going to be an issue. So we want to encode this into a differential equation, an equation involving a function and its derivatives. And so acceleration is a second derivative of position. Acceleration is a second derivative of position. And our statement is that this is a constant function. I'm going to write negative g because that's what we do in most physics classes. We say up is the positive velocities and down is negative velocities. And the gravity is making our velocity go towards down. So if we're going up, gravity will slow us down. If we're going down, gravity will speed us up. So by writing negative g, we're saying up is positive velocity. It doesn't have to be this way. If we did it backwards, then it would just be backwards. Down can be positive just as well. I could draw the whole graph left and right. But we just kind of agree to some shit, you know? So acceleration due to gravity is constant. We're saying that the second derivative is just whatever this number is. It's 32 in feet per second and 9.8 in meters feet per second squared and 9.8 in meters per second squared. I don't have any other values. So if we want to figure out what our velocity is at time, so our acceleration at time t is always just whatever this is, minus g. Our acceleration is always sending us towards Earth. Our velocity is going to be increasing towards Earth. If we want to know what our velocity is at a function of time, as a function of time, if I integrate my second derivative, oops. This morning I was writing triple integrals and I used S. So I'm like, oh, integral. And I'm like, oh, triple integrals. I'm like, oh, no. That's not what we're doing. So if I integrate my second derivative with respect to time, I will end up with my velocity, my first derivative, or my velocity. And if I integrate g with respect to time, I get g times t. The derivative is constant, so our function must be linear. When we integrate, we always have this plus c, we have a constant. Because when we take derivatives, the derivative of every constant is equal to 0. So we don't know what constant we started with. There's two derivatives, so we're going to be taking two integrals. So I'm going to need two constants. So I'll call this c sub 1. Now let's look at what's going on. This is going to be a function that gives our velocity at time t. This minus gt is just gravity. We apply gravity for every second, and we subtract that from this c1. If we plug in t equals 0, that'll be our velocity at time 0, and that will be the value of c1. So notice that v of 0, I use green for go because it's velocity. So if I do v of 0, so we see that c1 is our velocity at time 0. So now we have an interpretation. Since we have the problem in context, we can come up with an interpretation for what the constant of integration is. We don't always get to do this. I don't know what the value is, not important. I know what it represents. So c1 is our velocity at time 0. Sometimes we'll refer to this as our initial velocity. And then we'll abbreviate this by saying v sub 0 or v naught. We could also say v sub 0. Or v naught, something that we inherited from the British. If we integrate again, this will give us our position, and this will be a very familiar equation that we see all the time. So if we integrate our velocity, if we integrate a first derivative with respect to time, we'll be at our original function. So now that we have a function for v, we can integrate that and get our function for s, for position. So s of t will be, we'll integrate the minus gt, so minus a half gt squared. We'll integrate the v naught plus v naught times t plus some constant. And then the same thing happens. If we plug 0 in for t, we'll know what's going on at time t equals 0. When we plug in 0, since it's a polynomial, all we're left with is the constant, c2. Because this is a problem about gravity, and gravity is just going up and down, we're going to refer to our position as height. So this is our height at time t equals 0. Otherwise known as initial height. And we'll write it as S sub 0. Or S. There we go. S naught, or S sub 0. I used to make the Mortal Kombat reference when I said sub 0, but then I stopped because I thought Mortal Kombat had gone away. And then I guess Mortal Kombat is still a thing. Don't know when Mortal Kombat, no, Mortal Kombat as a video game has had many versions, but the original version is older than almost everybody in this room. Mortal Kombat, the original one came out there, and one person in this room was alive, and it was me, and I was in high school. That's how long ago Mortal Kombat started. And it's still going. At least it's gone in multiple versions. There's that. If you play the original Mortal Kombat, you'll be super disappointed considering where games are now. But that's beside the point. And I won't make fun of you. Because if I make fun of people for playing old games, all you have to do is say, motherfucker, you still play Skyrim from every now and then. Fair. Fair. What are we talking about? Oh, yes. So we end up with our height at time t. And this is very common. We know that height in projectile motion is a quadratic function. Quadratic because our second derivative is acceleration. And in projectile motion, the only acceleration is due to gravity. Acceleration due to gravity is constant, as long as we're staying relatively close to our Earth. Two gravity numbers that you should know. 32 feet per second squared. I'm not sure how relevant this one still is. Or 9.8 meters per second squared. Questions? Some physics questions that come up. Notice that I'm talking about the height, and the initial upward velocity is 10 meters per second. So we're going to make a height function out of this. If our initial velocity is, say, if we have some initial velocity, but it's launched at an angle, then we just care about the vertical component. So so this upward takes out the middleman. To avoid having to do any trig. If we have velocity at an angle, we have a velocity that makes an angle of theta with the horizontal. We only care about the upward component of this velocity. So if we have velocity at some angle, some of that velocity is going horizontal and some of that velocity is going vertical. And we can just break it into parts, into components, a horizontal components, and a vertical component. It's fine. And we just make this little right triangle. So what's our horizontal component going to be? Which trig function uses that one? Our horizontal and vertical components are just going to be some multiple, some scalar multiple of our overall velocity at an angle. And since the v horizontal is adjacent to the angle, horizontal is v naught times the cosine of theta, and our vertical component is v naught times the sine of theta. So if I said the initial velocity is 10 meters per second at an angle of 45 degrees, and we would have to break that into components and just grab the vertical one, because that's what this function is about. That's what gravity cares about. Gravity cares about this one. So gravity only wants that one. But if I say the initial upward velocity is 10 meters per second, I have cut out the middleman. So I don't have to tell you what the angle is, so you don't have to do the calculation. I'll come up with some weird irrational number for your velocity. Or I just do 30 degrees, so we'll just get a half. It's convenient. So the sad part about this problem is that we've already done this problem. We've done an infinite number of problems. On the previous page of notes, we did an infinite number of problems. We had solved this projectile motion problem. All my distance and my velocity are all using meters and seconds, so I'm going to list as my gravity. So for this problem, gravity is going to be 9.8 meters per second squared. Oh, oops. If I don't state where the problem is taking place, just assume that it's on Earth. So that would be a real jerk move if I make you do the problem with 9.8 meters per second squared. And I say, haha, suckers, this problem took place on the moon. That would just be cheating on my part. I could do the super jerk moves. Like, this problem takes place on Phobos. And you're like, oh, what the hell is that? It's like, oh, it's one of the moons of Mars. Like, oh, great, what's gravity there? It's like, oh, I'll tell you the mass of Phobos. How about that? And you're like, oh, son of a bitch, you're just making me look up more shit. So the sad part about this problem is that we've got this problem all locked up. We know exactly what's going to happen. We can write the position at any time. We can write the position at any time. We can write the velocity at any time. Acceleration is going to be constant. But let's see how things interact. S of t is going to be negative 4.9 t squared plus 10t plus our initial height of 30 meters. Our velocity at any time t will be negative 9.8 t to the first plus 10, just like we predicted. This will be in meters per second. And our acceleration at any time t is going to be a constant 9.8 meters per second squared. It makes sense that these are the units that came up because S is in meters and T is in seconds. So delta S over delta T would be meters divided by seconds. Our V is meters per second and our T is in seconds. So our units for A, the derivative of V, will be meters per second per second. One thing I didn't point out on the previous problem, that our second derivative units are in meters per second squared. And our dt is in seconds. Remember, integration is multiplication where one of the factors is continuously variable. So it's just a multiplication of our acceleration multiplied by time. One of the seconds cancel out and give us meters per second. And the same thing happens with S prime. S prime is measured in meters per second, and dt is measured in seconds. So I have meters per second, a rate, times dt, a time. The seconds cancel out, and I get a distance in meters. So the units are helping us out. So we've got this problem completely sorted out, which is the boring part, but let's think about the position and the velocity at 3 seconds. S of 3 and V of 3. This will be how high we are and how fast we are going at 3 seconds. This is why I was going to do the problem in foots. Or make Earth just bigger, just bigger enough so that gravity just becomes a nice 10. I was originally not going to care about these numbers, but so what we can see is after 3 seconds, our height, we are at a height of 15.9 and our velocity is negative 19.4. So at 3 seconds, we have gone up a little bit and then fallen past wherever we started. And we're only at a height of 15.9 meters and we're falling at a velocity of 19.4 meters per second. I said falling because we have a negative velocity. Let's take a look at our definite integral. Let's write down a definite integral. Say the integral from 0 to 3 of v of t dt. And interpret what this would represent. V of t is the rate of the rate of change of our height. So this is how much our height will change from t equals 0 to t equals 3 seconds. What should this value be? Based on the information that we have up here. Like I said, this is a completely solved problem, but we want to learn to read different mathematical symbols. So I write the definite integral from 0 to 3 of v of t dt. V of t is the rate of change of position, or the rate of change of our height in this case with respect to time. So this definite integral will represent how much our position or our height has changed, starting at t equals 0, ending at t equals 3. And without calculation, we can figure out what that is based on the information we have up here. The fundamental theorem of calculus says that this would be s of 3 minus s of 0. What is s of 3? Well, we have that. That's 15.9 meters. And s of 0, our initial height was 30 meters. So we get 14.1. So this says from 0 seconds to 3 seconds, our height would have changed by, height would have decreased by 14.1 meters total. Questions? Here's the relationship between position, velocity, and acceleration as functions of time. We differentiate in one direction, we can integrate in the other direction. We can interpret what the constants of integration are based on the context of the problem. Any questions? Comments? Snod Lamar? Other common questions, if you were waiting for them, is when is the maximum, when does the object reach its maximum height, and how high is that? Also, when does the object land on the presumable ground? When is the height equal to 0? And how fast is it going at that point? Those are your common questions that go along with this one. Another good one might be, the object clearly has gone up and then will start to fall. When is the object back at a height of 30 meters? All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.